know logistic curves as the lovable creatures who spend their days frolicking in the sunshine with their close friends, the exponential curves, and their cousins, the logarithmic curves. But what most math students don't realize is that these fun-loving animals have a life that transcends even our own. Observe the joy, the guilt, the regret, the pain, the love they feel. This video will explain the biology behind the creature we all know and love, the logistic function. This is a logistic curve. Looking at it, the first thing you'll probably notice is its distinctive S shape. This unique structure is brought about by the curve's reliance upon asymptotes. As x decreases, y approaches 0. On the other hand, as x increases, y approaches this pink asymptote. For the sake of simplicity, let's define this line as y equals a. So in order to model this graph, we need a function with two asymptotes, one at y equals 0 and one at y equals a. These are horizontal asymptotes. Horizontal asymptotes, you may recall, are y values for which there is no x value because the x value is undefined, usually brought about by dividing by 0. So this means that in our function we should be able to plug 0 in for y and get out some kind of undefined answer. We should also be able to do this with a. Most functions with multiple asymptotes have a denominator with some kind of sum. Let's assume for simplicity's sake that our function conforms to these norms. So at this point we can assume that our function is in the format y equals a over some number plus some f of x, and that it has two asymptotes, one at y equals 0 and one at y equals a. If you think about it, n can be any number whatsoever so long as you compensate in the f of x. But let's choose 1 because it's such a nice number. So our equation becomes y equals a over 1 plus f of x. From this point, we can figure out f of x using the asymptotes. When we plug in 0 for y, we know that we should get out an undefined answer. Cross multiply, and already we're dividing by 0, which means that we know that y equals 0 is indeed an asymptote. And then we can plug in a for y as well, and cross multiply again to get 1 equals 1 plus f of x. Subtract 1 from both sides, and you get 0 equals f of x, which means that y equals 0 needs to be an asymptote of f of x. You'll remember from our logistic curve that as x increases, y also increases, and as x decreases, y decreases. But because f of x is part of the denominator of this function, the opposite is true. As x increases, f of x decreases, and as x decreases, f of x increases. Plus, f of x has an asymptote at y equals 0. Hey, isn't this beginning to sound a lot like an exponential decay function? Exponential decay functions, of course, have a format of f of x equals b times a constant e to the negative dx, which you can plug into our equation to get y equals a over 1 plus b times e to the negative dx, which is cool and everything, but it's not really helpful when you're given a problem that looks like this. So we're going to try to find a generalized formula for the points 0, f, g, h, and of course the limit a. First, we can plug the point 0, f into our formula. 0 for x and f for y. So then we get f equals a over 1 plus b times e to the negative d times 0, and of course negative d times 0 is 0, and e to the 0 is 1. So then that just comes out to be f equals a over 1 plus b, cross multiply again, and then 1 plus b equals a over f, subtract 1 from both sides, and therefore b equals a over f minus 1. Now we can plug b back into the equation, so y equals a over 1 plus a over f minus 1 times the constant e to the negative dx. And now we can try to solve for d in terms of the other variables. So now we can plug the point g, h into the equation. So h equals a over 1 plus a over f minus 1 times e to the negative dg. And then we can cross multiply. So a over h equals 1 plus a over f minus 1 times e to the negative dg. Now we can subtract 1 from both sides, so a over h minus 1 equals a over f minus 1 times e to the negative dg. Divide both sides by a over f minus 1. Now we can convert this into a logarithm, so log base e of a over h minus 1 over a over f minus 1 equals negative dg, and of course log base e is also known as ln. So then we divide both sides by negative g, so d equals negative ln of a over h minus 1 over a over f minus 1 all over g, which is really pretty, right? However, this is probably going to be cleaned up when we actually plug it into the equation. First we have to multiply it by negative x. The negative signs cancel out, so then it becomes x over g times the ln of a over h minus 1 over a over f minus 1. We know what to do with the coefficient of a logarithm. So this becomes the ln of a over h minus 1 over a over f minus 1 raised to the x over g. Of course, e is going to be raised to this, and again, we know that e to the ln of something equals the something. So this just comes out to be a over h minus 1 over a over f minus 1 raised to the x over g power. And then we can plug this into the entire equation to get y equals a over 1 plus a over f minus 1 times a over h minus 1 over a over f minus 1 to the x over g, which looks incredibly ugly, but when you actually apply it, it comes out rather nicely. To demonstrate this, let's choose a little example. Let's say that the limit is 10 and that it passes through points 0, 2, and 6, 5. A over f minus 1 is 10 over 2 minus 1, which is 5 minus 1, or 4. And then a over h minus 1 is 10 over 5 minus 1, which is 2 minus 1, which is 1. So this all comes out to be y equals 10 over 1 plus 4 times 1/4 to the x over 6, which actually is pretty nice. So now you understand how to apply this formula as well as its derivation, which will hopefully allow you to fully appreciate the awesomosity of the fun-loving creature we all know and adore, the logistic function. Thank you.